China's newest chassis, Breakthrough, has already made aluminum look heavy and outdated. One structural component just dropped nearly 17 pounds of weight per corner of the car. You heard that right, 17 pounds gone, about the same as removing a full case of bottled water from every single wheel well. And that is not even the part that should surprise you most. Here is the part that blows people's minds. The material achieving this is not some exotic alloy locked away in a lab. It is already rolling off a real production line today. Hit a quick like and subscribe so you don't miss the next one. By the end of this video, you are going to understand exactly how this replacement pulled off what aluminum never could in 70 years. But to see why that matters, you first have to understand what aluminum got right. For 70 years, the aluminum stamping and welding line has been the quiet backbone of the entire auto industry, and it earned that position the hard way, through decades of refinement rather than luck. Sheet aluminum could be rolled, stamped, and shaped by presses that cost a fraction of what an integrated casting system demands, which meant almost any manufacturer on Earth, large or small, could realistically enter the business and compete on equal footing. Engineers love it because a cracked panel can be cut out and replaced without touching the rest of the car. Manufacturers love it because a stamping line can be reconfigured for a brand new model in a matter of weeks, not years, saving enormous amounts of capital. Governments love it because it spreads jobs across dozens of small supplier plants instead of concentrating all of them inside a single automated hall. Picture a jigsaw puzzle with more than 70 separate pieces, each one shaped, welded, and bolted into place by hand or by robot arm. That is the traditional rear floor of an electric sedan, and for decades, it was the smartest way anyone knew how to build one. It is not brute force manufacturing, not guesswork, and not a shortcut. It is nearly a century of engineering discipline compressed into every single weld on that floor. So if this system was so well designed, so widely trusted, and so deeply embedded in 100 years of manufacturing knowledge, you have to ask the obvious question: why didn't anyone solve this sooner? Here is the part that most people never think about. The very thing that made the old process so flexible is also what quietly made it so slow and so heavy. 72 individual parts do not simply appear on their own. They are formed, trimmed, positioned, and joined together at 840 separate welding points, and each one of those points is a possible source of error, a source of added weight, and a source of added time on the line. Picture 840 tiny rivets holding together something the size of a dining room table, each one a place the whole structure could eventually loosen. That number alone should tell you this was never a simple assembly job. It was a small, repetitive industrial choreography performed on every single car that rolled off the line, 60 times an hour, all day long. Something inside that choreography was quietly waiting to be replaced, and it was about to be. That choreography has a structural cost, and it is not the one most people assume when they picture a factory floor. 840 welding points are not just labor. They are 840 potential stress risers, 840 individual places where the metal has been heated, cooled, and reshaped in ways it was never naturally meant to hold. This is not about how many parts a car has. It is about how many places a car has been asked to trust a joint instead of trusting a single continuous structure. Traditional stamped and welded rear floors take close to a full hour to fully assemble once every station on the line is included, and every one of those 60 minutes is paid for 3 times over in labor, in floor space, and in machinery that has to keep running around the clock. Picture an assembly hall the length of 3 football fields end to end, packed with robots and workers doing nothing but positioning and welding metal for 60 straight minutes on every single car, all day, every day, all year. That labor cost does not simply disappear into the ether. It gets folded directly into the sticker price of every single vehicle that rolls off the line, adding hundreds of dollars nobody ever sees itemized on the window sticker. Not a rounding error, not a footnote, not a cost anyone could quietly absorb forever. It was a structural tax the entire industry had simply learned to live with, generation after generation, model year after model year. Here is the detail that puts everything into perspective. None of this was ever a secret inside the industry. Every major automaker on Earth knew that stamping and welding was reaching its practical limits, and several had quietly experimented with large single-piece castings for over a decade without making the idea work at true production scale. The alloys kept cracking under their own weight during cooling. The molds kept failing under the enormous pressure needed to fill a structure that large and that thin without leaving hidden voids inside the metal. Billions of dollars in prototype tooling were quietly written off across the industry, and few outside the engineering teams themselves ever heard a word about it. In 2024, a team inside Xiaomi's Automotive division began answering that exact question with data that was harder to dismiss than anything the field had seen before. That team was not working alone in a vacuum. It was building on ideas Tesla had already proven were physically possible, using die-casting machines developed in close partnership with the Chinese industrial press manufacturer, Haitian. The core idea sounds almost too simple once you actually hear it explained plainly. Instead of hand-selecting an existing aluminum alloy off the shelf and forcing it to survive a giant casting process it was never designed for, Xiaomi's engineers used an artificial intelligence system to search through millions of possible alloy combinations for one specific, narrow property: strength, without any heat treatment at all. Previous attempts had failed for a very specific, very physical reason. Because standard aluminum alloys need hours of post-casting heating and cooling to reach usable strength, and at the scale of a full rear floor, that thermal cycling warped the part badly before it ever left the oven. Entire prototype floors came out of ovens twisted just enough to fail final inspection, over and over, at a cost of months of wasted development time. Think of it like baking a dinner plate-sized piece of bread versus baking one the size of an entire dining table. The bigger the object gets, the more unevenly it cooks all the way through, and the more it cracks and warps as it finally cools down. Xiaomi's answer was a proprietary blend, now called Xiaomi Titan Alloy, built from more than 10 separate elements including aluminum, silicon, rare earth metals, and zirconium, engineered from the ground up to reach structural strength straight out of the mold, with roughly 30% of that composition still being aluminum itself, just no longer working alone. Here is what makes this incredibly exciting. Because the part never needs that oven cycle at all. It comes out of the press already true to its intended shape, with none of the warping that doomed every earlier attempt at this scale. Paired with a 9,100-ton press, a clamping force roughly equivalent to stacking 6 fully loaded Boeing 747 aircraft on top of a single mold, the system could finally hold a casting this large steady long enough for it to solidify correctly, all the way through, without the mold flexing or the metal separating unevenly inside it. That is not a small tweak. That is not a modest improvement. It is not an incremental fix at all. It is a wholly different manufacturing category entirely, built from first principles. Here is the honest limitation, stated plainly and clearly with a real number attached to it. Once that rear structure is cast as one solid piece, it can no longer be sectioned, straightened, or partially replaced the way a stamped panel always could be. And repair engineers have confirmed that even localized damage near a suspension mount can propagate a hairline crack through the entire casting. But here is what that number actually means in practice. For the vast majority of drivers, a fender bender or a minor rear impact never actually reaches the structural casting at all. It stops well short, at the bumper, the crumple zone, or the outer panel, all of which remain separate, bolted on, replaceable parts, rather than being fused permanently into the casting itself. The honest limitation applies almost entirely to the small minority of collisions serious enough to reach the frame itself, and in those specific cases, traditional stamped floors were frequently written off as total losses too. This is not a story about a flawless part, and it is not a story about a fragile one either. It is a story about a deliberate trade a manufacturer made with its eyes wide open. Now for the unexpected advantage nobody predicted going into this. Because there are no welding seams left to transmit road vibration, the cabin measures roughly 2 decibels quieter on rough pavement, which is close to the difference between a normal conversation and one held in hushed tones across a kitchen table. The casting also holds up under fatigue testing to distances beyond 1.2 million miles, more than 10 times the distance a traditional welded floor is expected to survive before joint fatigue quietly sets in. Enough driving, in theory, to circle the entire planet nearly 50 times over without failing. There is a non-obvious application this unlocks today. High-mileage commercial fleets and ride-hailing operators, where structural longevity matters more than almost any other single spec, are already among the very first customers lining up for vehicles built this way. Here is what most people get wrong about durability claims like this one. They assume a part built to last longer must also be easier to fix, and here, exactly the opposite turns out to be true. The question was no longer whether a single-piece casting could survive real-world use. The question was how fast the rest of the industry could actually catch up. The answer arrived at a real factory inside the Beijing Economic and Technological Development Zone in 2024, where Xiaomi's production line began turning out finished vehicles at a rate of 1 car every 76 seconds, with each individual rear floor casting completed in roughly 100 seconds flat. If this surprised you, the next part is going to be even harder to believe. Hit subscribe now so you're there when we cover it. The field matched the forecast almost exactly, and that match matters enormously in an industry where lab prototypes routinely fail the moment they meet a real assembly line running 24 hours a day, every day, at full production speed, under real heat, real dust, and real human error. A prototype can be babied by a small team of specialists in a clean room. A production line cannot. It has to work the same way on the 10,000th car as it did on the first one. A production engineer working close to the line put it plainly and simply. We stopped thinking of the floor as 72 separate problems and started thinking of it as one. Part of why this scaled so smoothly is basic compatibility. The 9,100-ton press slots directly into an existing automated factory, alongside more than 700 robots and over 180 autonomous delivery units already used to move other parts of the car, meaning the rest of the plant never needed to be rebuilt from scratch, and the factory could keep running while the new system was phased in section by section. Xiaomi has also made portions of its production and defect detection data available through supplier and industry disclosures, including a vision inspection system checking each and every casting with an accuracy rate above 99.9%. An unusually transparent look into a process manufacturers have historically kept locked tightly behind closed doors, far from public view and far from independent audit. It started with one single application, where production speed and structural rigidity simply mattered more than the repair cost limitation. Then it spread outward from there, into performance trims, into commercial fleet orders, into an entire second and third generation of the casting system, each one lighter and faster to produce than the last. Suppliers who once specialized only in stamped panels began retraining their own engineers to work with the new alloy instead. The claim now had receipts, and the receipts kept coming. More than a dozen international patent families now cite Xiaomi's die-casting alloy chemistry and equipment design, filed across China, the United States, and the European Union. These are not academic citations sitting in a drawer somewhere. These are legal and financial commitments backed by real capital. Tesla, the company that first proved large-scale casting was even viable, has continued expanding its own 6,000 to 9,000 ton systems across its Texas and Shanghai plants. Zeekr adopted a 7,200 ton press of its own for a similar integrated floor section, betting a significant slice of its production budget on the same underlying approach. XPeng went further still, deploying the world's only 12,000 ton integrated die casting machine currently in commercial use anywhere, with plans publicly announced to expand towards 16,000 tons of clamping force within the next few years. Chinese industrial policy has directly and deliberately accelerated this shift as well, with several local governments offering manufacturing subsidies tied specifically to automation and energy efficiency benchmarks that heavily favor large-scale casting over traditional stamping lines. In any market where a 45% cut in assembly time translates directly into a lower sticker price for the buyer, that advantage stops being a trend worth watching from a distance. It becomes a competitive pressure no serious company can afford to ignore for long, no matter how comfortable its existing factories are. Here is what most people get wrong about this entire shift. It is not really a contest between individual companies anymore. It is a contest between two entirely different philosophies of how a car should be built, one modular and repair-friendly, the other integrated and production-friendly. Legacy manufacturers, including Volkswagen, General Motors, and Ford, still rely almost entirely on stamping and welding across their global plants that in many cases have run the same way since before some of their current engineers were born. And shifting to large-scale casting would require billions of dollars in new presses, new alloys, and entirely new supplier relationships built from the ground up. That is not a small decision for a company sitting on top of 100 years of existing infrastructure, existing supplier contracts, and existing worker training programs built entirely around the old process. And notably, Xiaomi has continued publishing incremental defect rate and casting yield figures through supplier channels rather than sealing that data away, letting outside engineers, suppliers, and even competitors watch the process mature in something close to real time, quarter after quarter. If this scales the way current production numbers suggest, integrated casting could eventually replace stamped rear floors across a meaningful share of the roughly 90 million cars built worldwide every single year, a shift on the scale of an entire country, changing how it manufactures nearly everything it drives, all at once. There is a secondary benefit worth naming directly and clearly. Skipping the post-casting heat treatment cycle can cut the energy used to produce each individual rear floor by a double-digit %, since that oven stage was traditionally one of the single most energy-intensive steps in the entire stamping process. Across 90 million cars a year, even a modest energy saving per vehicle adds up to enough electricity to power a mid-sized city for months. But turning a promising technology into a global standard is a long road, and it is important to be honest about where that road gets genuinely difficult. Insurers in multiple markets have already begun raising premiums on vehicles with single-piece rear castings, citing the far higher cost of a full structure replacement after serious damage. Legacy automakers face retooling costs that industry analysts estimate in the billions of dollars per major manufacturing plant, spread across dozens of plants worldwide. Skilled labor trained for decades in stamping and welding will need real, structured retraining for a fundamentally different production process, a transition that will not happen overnight or without real cost. The raw materials and specialized presses required are currently concentrated in a small number of Chinese suppliers, creating a supply chain dependency few Western manufacturers are comfortable with today. Emerging right-to-repair regulations in the European Union could directly conflict with a manufacturing philosophy built around structural components that were never designed to be repaired in the first place. Here is the part most coverage of this topic leaves out entirely. None of these obstacles are theoretical, and none of them will resolve themselves without deliberate decisions being made in boardrooms and legislatures over the next several years. None of these challenges change what the engineering shows is possible. They define the gap between what is technically achievable and what will actually happen at scale. Closing that gap is an investment problem, a policy problem, and a coordination problem as much as a manufacturing one. The researchers who developed this alloy gave the world a tool. Whether the world picks it up at the speed the market demands is a different question entirely. The story of integrated die casting is ultimately the story of what human civilization can build, and where it can build it, and who gets to build it first. Right now, that story is concentrated almost entirely in China, where vertically integrated supply chains for batteries, alloys, and casting equipment sit inside a single manufacturing ecosystem, a level of coordination that smaller or developing automotive markets simply do not have access to yet. That leaves manufacturers in regions like Southeast Asia, South America, and parts of Eastern Europe watching this transition largely from the outside, unable to compete on price or production speed until the equipment and alloy expertise spreads further than it currently has. What is genuinely new, not incrementally better, but categorically different, is a manufacturing alloy engineered from the ground up to skip an entire industrial step that every aluminum part before it was simply assumed to need. That is not a minor improvement. It is a different category of solution entirely. The researchers who published this work gave the world a tool. Whether the world picks it up at the speed the auto industry's cost pressures demand is a separate question, one that belongs to policymakers, investors, and manufacturers as much as it belongs to scientists and engineers. That is new. And because a car built today will very likely still be on the road in 15 or 20 years, decisions being made on factory floors right now about how vehicles get built will quietly shape repair costs, insurance markets, and resale values for an entire generation of drivers who have not even bought their first electric car yet. If a manufacturing decision that specific can already reshape how a car gets fixed after a simple fender bender, it is worth asking what happens when the vehicle itself no longer needs a chassis built for driving on roads at all. And that question is exactly the subject of our next video. China's plan to switch to flying cars by 2027 left the auto industry in panic. The link is right in the description. If this changed how you think about the cars sitting in your driveway, hit that like button and subscribe so you never miss what comes next. Turn on notifications. We publish every week. Now I want to hear from you directly in the comments. Would you drive a car that is faster, quieter, and cheaper to build, but effectively totaled after any serious rear-end collision? Team efficiency or team repairability?